All right, we're continuing in our study of refrigeration, and we have another cycle, another method of accomplishing refrigeration. It's gas refrigeration. It's basically a Brayton cycle run backwards. So what was our Brayton cycle? We had a compressor, then we came up to a burner where we added heat, Q in, and then we went through a turbine to expand it to make some work. Some of that work came back to run the compressor, some of it was above and beyond what needed to be run to run the compressor, hence we had net work out. And then you came into a heat exchanger in which you rejected some heat out of the cycle, and that was it. Now, somebody says, how can that accomplish refrigeration? I understand how that Brayton cycle produced power. How can that accomplish refrigeration? Well, turn it around, run it backwards, run it this way. Well, now you're going to go, it's not going to be a turbine anymore, it's going to be a compressor. It's going to run backwards through it. And here, instead of having Q in, we're going to run it backwards. We're going to have Q reject or Q out. And here, instead of a compressor, we're going to run it through a turbine. So we're going this way through the cycle. We're changing it. And here, a heat exchanger, you're going to have the Q in. Okay. Where would we have our refrigeration? Where would we have that cooling? Isn't this our Q cooling? Isn't that our refrigeration? Yeah, that's where we're going to have it. Picking up heat out of a low temperature with a low temperature. And then where are we having it dumped at? Well, we're dumping it to the ambient Q out. And instead of having net work out of this cycle, we have to have net work in. The turbine produces some power or work that can help drive that compressor, but not enough, and so we're going to have a net supply. So that's what we do. We actually, this is kind of funny. You can turn that cycle around, that Brayton cycle around, and you have a refrigeration cycle. It's not very common, but it can be used. Okay, so here's a sketch of what I just described, the compressor. You have some net power to run the cycle. You do have some output from the turbine to help drive that compressor, but you still have to supply more. This is a heat rejection, Q out of the system at high temperature. This is our Q cooling or into, and that's our refrigeration. If you just said, I know how to do an open control volume analysis of the compressor, an open or control volume analysis of that heat exchanger, likewise for the turbine, you get that this Q out is going to be H2 minus H3. The work to run the compressor, H2 minus H1. The Q in will be H1 minus H4. And the work out of the turbine on a per unit mass basis, everything here is on a per unit mass basis, is H3 minus H4. All those are positive entities because I know the direction of them. So the whole game is going to be getting those enthalpies to analyze this cycle. Very, very similar to what you've already done with the Brayton power cycle. So let's solve a problem. So we have a gas refrigeration cycle. When you see that gas, you're thinking ideal gas, Brayton refrigeration cycle. Using what is a working fluid? Air, unless you're told otherwise. Somebody could specify, oh, use this carbon monoxide, carbon dioxide, nitrogen, or whatever, but if it's not specified, it's air. It has a compressor pressure ratio of 2. It has an inlet to the compressor, has a pressure of 200 kilopascal and a temperature of 310. The temperature at the turbine inlet, where is that again? Well, right here, this is the turbine inlet, so that's the temperature at state 3 is 325 Kelvin. The compressor and the turbine have some isentropic efficiencies, so a little extra work there analyzing the inefficiency of the compressor and the turbine. Assuming variable specific heats. What do they mean by that? You need to use the table. That's how we evaluate air properties with assuming or accounting for variable specific heat, temperature dependent specific heats. That table was in our textbook, table A22. Okay, determine the net work input per unit mass flow. So it'll be the W net, which is how much the compressor needs minus how much that turbine produces, all on a per unit mass basis. And then what is the cooling per unit mass? Something like lowercase q, refrigeration effect or cooling, something like that, some subscripts that make sense for this problem. And then the coefficient of performance, this is a refrigeration cycle. It's what we desired. Oh, we desired a lot of cooling. That's the answer for part B. And we have to pay for the power. So we have to provide the work for the operation of that cycle. So the answer for part B divided by the answer from part A. That's the answer for part C. You ready to solve this problem? Let's solve it in Excel. Give me a minute and I'll set up my computer. You have all the pertinent information recorded, right? So when I move away from this slide, I don't have to come back to it. All right. So let's go to Excel. This is my way of solving this type of problem. I like to type a comment in cell A1, so it's gas, refrig with air as a working fluid, with air, something like that. Good enough. And then we're going to put a table of properties, but I like to put some of the inputs up front. I know I'm going to use the pressure ratio. And for this problem, the pressure ratio is 2. That's not a lot of boost across the compressor, but it's enough to accomplish refrigeration. Okay, so we're going to have a table of properties. Let's put state. Then we'll put our pressure at each state. Let's put our temperature in Kelvin for each state. Our enthalpy, which is critical. That's really what we want, kilojoules per kilogram. And because we're going to use those air tables, we're going to use this PR. It's a no-name parameter. It's found only for isentropic processes in table A22. Because we're given the pressure ratio information, we would use that column in table A22. All right, so we think about it. We come into the compressor state 1, and then it can go out 2S or 2 actual. I'll put 2 lines for state 2. I'll do it in a 2-step process. And then we go out of that heat exchanger, and now at state 3 it's ready to go into our turbine where it can be expanded to 4S or 4 actual. And that's it. That's all of our states. I like to clean this up by grabbing that and saying, go ahead and do it. What is that? Right formatted, right justified something. Otherwise it looks funny. Okay. So at state 1, it was 200 kilopascal going into our compressor, and the temperature was 310 Kelvin. True? Good. Now what we can do is we can get the enthalpy as a function of temperature for our air. There's our call. This is in the Excel file, that add-in that you can use or have used. And then I can get PR for, as a function of temperature for air, and I look it up. This is exactly what you would do by hand. You should do by hand as well so that you're familiar with it. You don't rely only on the software. At this point, you say, well, when we have an isentropic process, the ratio of PRs is equal to the ratio of the physical pressures. So the PR at the end of the isentropic process is the PR at the beginning times the pressure ratio, and so it's 3.1092. Now I can look up the temperature. That's T2S. So temperature is a function of PR for air, and I look it up. So the temperature would have gone from 310 to 377.6. too many digits on this, I grab the whole column and kind of clean it up a little bit. I think we'll put just 0.1. So 377.6 Kelvin. Likewise, the same interpolation to get enthalpy as a function of PR. For air, oh yeah, this is lovely, just lovely. All right, what I'm just going to type it, F6. That'll work. Sometimes it's better just to type it. And I'm going to clean this up and fix my significant digits. So there you go. All right, what is the pressure? Well, it was 200 times that pressure ratio. Actually, I can do all the pressures. Isn't that the same pressure? And isn't that the same pressure? And then when we expand it after the turbine, isn't that back to 200? Isn't it back to 200? Sure. What did I do there? There, we fixed it. All right. So now I like to run it in a few steps to do the compressor efficiency. So the efficiency of the compressor was given to be 82%. All right. What I say is the work that the compressor needs to accomplish that pressure increase, if it had been isentropic, I now can calculate it's going to be this one minus that enthalpy. So the best compressor, if it had been reversible, adiabatic, actually the best compressor would be I cool it while I compress. But let's just say, you know, it's adiabatic and reversible. It would have required 68.2 kilojoules per kilogram. Well, what about the actual amount of work? This is where I like to break it into 3 steps so I don't make a mistake. Is because of irreversibilities, is the compressor going to require more than 68.2 or less than 68.2 kilojoules per kilogram? More. And so, whoops, why double equal sign? Put that divided by the efficiency. And then I pause, look at it. Well, clean this up a little bit. It'll require, what is that, 83.1? If you like, I like to maybe put kilojoules per kilogram to really emphasize that's what we're calculating over here. Okay, now I can come over here and I know the enthalpy at the actual exit of that compressor, don't I? It's how much? It was 310 coming in and it went up by 83.1. So there it is. It comes out a higher enthalpy. I had to put more work in because of irreversibilities. The temperature will be higher. The temperature is a function of enthalpy for air. Put that right there. It comes out at 393 instead of 288 Kelvin. It's hotter. And we don't need that piece of R at this point, so I'm going to leave that blank. The next piece of information was it's cooled in that heat exchanger from 392 down to 325. Wasn't that part of the problem? But now we're ready to put it into the turbine. So it's just like what we did going into the compressor. We're going to think about getting the H as a function of temperature. And now it's 325. And we get piece of R as a function of temperature for the air, 325. Now we're ready to expand isentropically. I'll work on the piece of R. So that's that P divided by the pressure ratio. Goes down to 0.91, blah, blah, blah. Do some interpolation. So we calculate that the enthalpy is a function of PR for air. Oh, come on now. Don't. Oh, this is embarrassing. Okay, F9 it is. Done. And then this one is temperature as a function of PR for air, and go get that PR. So it would have expanded down, and you can see now it's cold. If it would have been a perfect isentropic expansion in that turbine. Well, we do the same thing. We come over here and we say, well, what's the isentropic efficiency for the turbine? This case it was 85, right? And I don't like not seeing more digits on that. 80 something and 80 something. So 82 and 85. Okay. So the work that the turbine would produce if it would have been isentropic expansion, we now can calculate. It came in at 325.3 and would have left at 266. So we would have gotten 58.7 kilojoules per kilogram out. But because of the irreversibilities, the work that the turbine actual, is it going to be greater or less than 58.7? Less. And so you basically multiply that by the isentropic efficiency, just using the definition of the isentropic efficiency. So it came in at 325.3, but there was a 49.9 drop, and there, that's the actual enthalpy that it comes out at. I can calculate the temperature. Temperature is a function of enthalpy, and that one works. So it comes out at 275. So it's going to be heated in that heat exchanger from 275 back to 310, and that's where you get the refrigeration. Let me ask you a question. Am I going too fast or too slow or just right? Too fast? Too slow? Just right. Okay. So we come over here, we're going to make a table of our energy transfers for each component. So what are our components? Well, the first component would be our turbine or compressor. Put compressor. Then our heat exchanger where we reject heat, and then our turbine, and then our heat exchanger where we are providing refrigeration. All right? All right. And then we're going to have Q in kilojoules per kilogram for each component. Is there a heat transfer per unit mass flow through it, as well as work in kilojoules per kilogram. This table you've seen before, it has 8 entities. 4 of them are 0. So let's put the zeros in. So the compressor, adiabatic, turbine, adiabatic. Both heat exchangers, no work. And because I want to sum the columns, I want to get the sign convention right, so I'm going to adopt our sign convention here. So for the compressor, I know I'm looking at the number over here. It's 83.1 kilojoules per kilogram, but it's into the compressor, so I'm going to put a minus and then go get that 83.1. Okay. How about for the turbine? Well, it just calculated 49.9 out. So if you want to do the sum, we can do that right here. The sum for the work per unit mass for each of the devices, and it's negative 33.2. The negative sign makes sense. It's power into the cycle or work into the cycle. Now let's go and do it, the heat rejection. Here, where's our heat rejection? We're going from state 2 to state 3. So because it's rejection, it's going to be a negative energy transfer. It's not into, but out of, this one. Whoops, I messed that up. It's this one, H3 minus H2. So we'll transfer out 68.0 kilojoules per kilogram. And then for the refrigeration, that's energy transfer into the fluid. And so it's H1 minus an H4. Makes sense? And we'll copy over this sum or just drag it or sum, just type it like that. And these two are, let's compare them. That's a lot of digits. They agree to 1, 2, 3, 4, 5, 6 digits. That makes sense. Don't need to show them all, but there you go. So we could put a table for our answers. For part A, we were interested in W net. And what is that equal to? It's equal to negative 33.1, isn't it? In kilojoules per kilogram. For part B, we're interested in Q cooling or refrigeration, and that's equal to 34.9. And the same units, kilojoules per kilogram. And for part C, we were interested in the COP, for the refrigeration cycle. That's the ratio. How much cooling did I get per how much work did I put in? Now, I want to probably put an absolute value on that just so I avoid a negative COP. And so the COP comes in at 1.05. Is that a high? No, it's not a high coefficient of performance. Do we see a lot of ideal gas Brayton cycle refrigeration in practice out there? No, we see a lot of vapor compression. You could use this. Why isn't it used more? Probably because of a low coefficient of performance, right? It's low COP. What would be an advantage? Well, it's pretty easy to get cold ideal gases, as long as you're just not down near the point at which you start to liquefy the oxygen or the nitrogen. So you can get pretty cold refrigeration using the ideal gas cycle. With that, I kind of give you the pluses and minuses. We solved the problem. We're good to go? All right, let's get out of Excel and jump back to our problem here. Here's the solution worked up in Excel for variable specific heats. What do you think's on the next slide? And not variable specific heats, but constant. And the answers are not very different. The answers are very similar. So you come over here and you do it for constant specific heats. There you would use the K for air ratio, K minus 1 over K. Use this value, C sub P, and it almost agrees to 3 significant digits. Instead of being negative 33.3 with variable specific heats, it was negative 33.2. Full credit either way. How's that? Make you happy? Yeah. 34.8 with variable, 34.9, and 1.05 and 1.04. Okay. For the exam, what does it require? Constant or variable or your choice? Variable. All right? Okay. Also, right now, where are the numbers, those sheets? Have they been circulated? Does anybody still need to see those sheets? Raise your hand. You need to see them? Somebody want to circulate, pass them down a set of numbers to them? Anybody else need to see the numbers? It's also typed up in Blackboard Learn. It's loaded up there. Well, this finishes our discussion of the air or the gas refrigeration cycle, the Brayton refrigeration cycle. I do have a question for you. Somebody says, when I had to drop from this high pressure to the low pressure, instead of using a turbine, which is probably expensive to buy, why don't we try to use an expansion valve? They're very cheap. We could reduce the cost of this air Brayton cycle if we replace the turbine with an expansion valve. So we still have our compressor, our heat exchanger to reject heat, heat exchanger to absorb heat. The question is if you replace that turbine with the expansion valve, will the system work or not work? And some discussion of why. So what I want you to do is I want you to answer this question. I'm going to pause, walk around, and you select A, B, or C, and then maybe prove or show me why your answer is the answer that you selected. Well, let me pick it up at this point. The one good way to analyze or answer this question is to think about the property diagram. And one of our favorite property diagrams is a temperature entropy property diagram. And we're very familiar with it. We have our low pressure and our high pressure, pH and PL. And we think about, first of all, I'm going to reproduce it for the Brayton gas power cycle. So for the power cycle, we started down here, we compressed it, we then heated it, we then expanded it, and then we cooled it. So this was the compressor, this was the burner, this was our turbine, and that envelope, that area enclosed, is a representation of the network. If you have some irreversibilities, they kick off that way. Okay, that's a good review. Now let's talk about gas refrigeration. Well, I'm going to basically kind of push it over here, even though I think about shifting that temperature scale down. And then we put it through the compressor, and then we put it through a heat exchanger to cool it, because that's what that heat exchanger up here from 2 to 3 is doing. So state 3 ends up right here. And then when we expand it through that turbine, it would be down to state 4, and from 4 to 1 we get our refrigeration, our Q refrigeration, right? That makes sense? Kind of showing it, instead of going clockwise, it's counterclockwise, 1 to 2 to 3 to 4 on a TS diagram. Now, if you had the inefficiency of the compressor, let's say the isentropic efficiency is not 100%, it's 98 or 96 or 90% or 80%. Where does state 2 drift off to? This is now 2S, and doesn't state 2 drift off like that? Yeah, right? And so let's think about the compressor. I'm sorry, the turbine. Over here you're still thinking turbine. Where is state 4 actual compared to 4S if I have some irreversibilities in the turbine? Isn't it kicked over like that? Yeah. And so state 4 may be here, 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 you know. And as you can see, as you get more and more, the lower the isentropic efficiency is of that turbine, then the temperature at 4 is going up, 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 and you get less of a potential refrigeration effect. All right. Well, guess what an expansion valve is? It's not just a very poor turbine, it is an extremely poor turbine. It's like a turbine with a 0% isentropic efficiency. You get no work out of that expansion valve. That's a very bad turbine. And so we go back and we say, we know that the pressure at 3 is greater than the pressure at 4, but when you get to an expansion valve, when you get to an extremely poor turbine, aha, H3 compared to H4, it's isenthalpic. I get no work out of the expansion valve. It's isenthalpic. I remember for an ideal gas, that the temperature, the enthalpy is a function of temperature only, right? And so guess what? At the worst case, where does state 4 continue to drift to? Horizontal line, constant temperature on a TS diagram. Okay, you now have some hot gas ready to go into this heat exchanger to pick up some. Is that going to work? Remember, we had 325 Kelvin. If you put it through an expansion valve, it's 325 Kelvin. Hold it, we started at 310 Kelvin. There's no refrigeration. So it's not going to work. It's just not going to work. There are some cases where if you really get the cooling and you bring 3 way down here, you could do it and then have some refrigeration effect, but not for the numbers we threw out. Okay? So there, that was a tough problem, right?